so far we are talking about positive numbers, fine. So, but the numbers may be negative also. So, next we will be looking into how to represent negative numbers. So, there are three distinct ways in which we represent negative numbers in computer systems. One is called sign magnitude representation, one is called 1's complement representation, the other one is 2's complement representation. So, we will be looking into these three types of representations in our next few classes. So, why do we need this what is the goal of this negative number system? So, the sign system, so this is simple. So, you just flip the sign bit. So, 0 is positive and 1 is negative. So, if you have to so you can say that in your system. So, if I have got say 4 bits. So, if I have got say 4 bits for representing numbers. So, in 4 bits I can represent the numbers 0 to 15, fine. Now, so in sign system what will happen is that, so we will have 4 plus 1 5 bits. So, these 4 bits are there, plus there will be extra bit which is for the sign part. Okay. Now, the sign part, so if it is 0, that means I am representing positive numbers. So, naturally I can represent the numbers plus 0 to plus 15. On the other hand, if this bit is 1, then the number is a negative number. So, you can say as if it is minus 0 to minus 15, because this value can go up to 15. So, of course, this is a bit confusing. So, I have got a plus 0 and a minus 0, but that is there, but apart from that, so this representation is very simple. So, if you have to convert a number from positive to negative or negative to positive, you just flip the sign bit of the number. So, that way the sign magnitude sign system. So, this is very simple and it can be used for representing the negative numbers. The 1's complement representation. So, it says that replace subtraction, the goal is to replace subtraction with addition. So, this subtraction process. So, we can do using addition, and here the idea is that we just flip every bit. So, if the number was originally say if I representing the number say plus 5 in 4 bit representation, if the number is 0 1 0 1, for representing minus 5 we just flip all the bits. So, it is 1 0 1 0. Okay. So, that is the it is the binary, it is the 1's complement number system. In 2's complement number system, so again we will be replacing addition subtraction with addition. So, addition of 1's complement and 1 produces the 2's complement. So, this is the 1's complement representation of minus 5. We are looking for 2's complement representation, then with that we have to add a 1. So, if you are adding a 1, so it is becoming 1 0 1 1. So, that is the 2's complement representation of minus 5. So, this way these number systems, they are the negative numbers can be represented and we can use them for computer representation. So, if we are for the 1's complement, the overall formula is like this. If the original number is x and you want to represent minus of x now, then for 1's complement the formula is 2 power n minus 1 minus x. So, for example, if we have got n equal to 4, then for the formula is 2 power 4 minus 1 minus x, 15 minus x. So, in binary, so what is happening is that this 15 is 1 1 1 1 minus the x b 3 b, suppose the x is b 3 b 2 b 1 b 0. So, essentially what will happen is that all bits will get flipped. So, you are subtracting. So, this will be it is subtracting from 1. So, the bits will be getting flipped. Okay. So, anything like say if I have got say 5, sorry, if I have got say 5, then in binary number system 4 bit binary it is 0 1 0 1. Now, say so I have got the numbers. So, I want to represent minus 5. So, as per this formula it says 1 1 1 1, from there I have to subtract 0 1 0 1. So, 1 minus 1 is 0, then this 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 0 is 1. So, what you get is 1 0 1 0, which is the 1's complement. So, if you take 1's complement of this, so all the bits are flipped. So, you get 1 0 1 0. So, you see that these two are same. these two are same. So, this is same as flipping all the bits. So, this is the mathematics. So, we have to take 2 power n minus 1 minus x, but ultimately it boils down to a very simple step, we just flip all the bits. Then in the 2's complement, the formula is 2 power n minus x. So, in 1's complement we have already done this one 2 power n minus 1 minus x. So, that is why it says that if we with 1's complement, if we add this 1, so this is 2 power n minus 1 minus x. So, if we add 1, then these 1's will cancel out. So, you will get 2 power n minus x, fine. So, we have got this 2's complement representation. So, n equal to 4, we have got 2 power 4 minus x. So, that is 16 minus x. So, so 16 is 1 0 0 0 0 minus this one. So, in the if we take the previous example that for the minus 5. So, it is 1 0 0 0 0 minus 0 0 1 0 1. Okay. So, 0 minus 1 is 1 with 1 carry. So, basically, so 0 minus 1 is 1. Now, 0 minus 0 is 0, 0 minus 1. So, there will be 1 carry. So, this 1 minus 0 will be, this will be 1, and then this then 0 minus 1 is 1 with a 1 carry, then 1 borrow rather. So, 1 minus 0 is so this is not anyway. So, this I will come back to this later. This is not very simple here. Anyway, so basically what we have to do is we have to do a bind. So, this is done by means of some addition. It is not it is not doing the subtraction in 2's complement form. So, that is why it created some problem. So, we will come back to this later, but this is basically flipping all the bits and taking adding 1 to that. So, in say if these are the numbers, so 0. So, in normal representation is 0 0 0, signed representation. So, this is 0, 1's complement representation is also 0, 2's complement is also 0. So, for up to this much there is no change. So, up to 7, since it is a 4 bit representation, up to 7 all are same, but when you go to 8, then you have got this 1 0 0 0. So, since the signed representation, so this will be using a sign bit. So, most significant bit is the sign bit. So, this part is 0. So, it represents minus 0. Similarly, 9 in the sign representation will be is minus 1, because these 3 bits represent 1. So, this sign bit is 1. So, this is minus 1. Similarly, this one is minus 2. So, this is minus 3, like that. In 1's complement form, so this 1 0 0 0, so that is your 15 minus x. So, 15 minus, so that is basically that 15 minus 8, that is 7, and that is a negative number. So, it is minus 7. So, the 15 minus 9 is 6, so that is minus 6. So, like that. In 2's complement number system, it is 16 minus x. So, it is 16 minus 8 is 8. So, this 1 0 0 0 0 is minus 8, 1 0 0 1 is minus 7, like that. So, this way from the formula you will directly get all these values, but the point that I would like to mention is the range of values that you can represent in the number system. So, in case of signed representation, so you can represent the numbers minus 7 to plus 7 in a 4 bit. If I give you only 4 bit, then you can represent the numbers minus 7 to plus 7. In 1's complement representation, your negative side you can go up to minus 7, and the positive side you can go up to plus 7. So, here also it is minus 7 to plus 7. In 2's complement representation, you can go from minus 8 to plus 7. So, this is something extra that we have got, and what has so in so I can say in general. So, if I have got say n bit, so n bit representation, then in this signed and this signed and this 1's complement. So, they are giving you you can represent numbers from minus 2 to the power n minus 1 to 2 to the power n minus 1. So, minus 2 to the power n minus 1, sorry, this is, that should be a minus 1. So, minus 2 to the power n minus 1, that is, for example, here it is 2 to the power n minus 1 minus 1. So, minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. So, if you put n equal to 4, so this is basically your minus 7 to plus 7. In 2's complement notation, in 2's complement, so you have got the range which is minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. Okay. So, for n equal to say n equal to 4, so we have got here minus 8 to plus 7. So, as you see here, so we can go up to minus 8 on the negative side and plus 7 on the positive side. On 1's complement and all, so I can go to minus 7 on the negative side at most and plus 7 on the positive side at most. Similarly, here also I can go up to minus 7 on the negative side and plus 7 on the positive side. So, why this thing has happened? You see that, so in 2's complement notation, so I can represent one number extra. So, this minus 2 to the power n minus 1, so this was not representable in 1's complement and signed representation, but it is representable in 2's complement form. This thing has happened because in case of this signed representation and 1's complement representation, so we are representing this plus 0 as well as minus 0. Similarly, in 1's complement also we are representing plus 0 as well as minus 0. So, the value 0, it has got two different representations in signed representation and 1's complement representation. So, that is actually I should say utilizing one extra code, okay, of the values. So, but in case of 2's complement you have got only 1 0. So, there is nothing like minus 0 in 2's complement notation. So, we have got one extra pattern, so which is being utilized to represent say one extra number. So, this this way we can have this 2's complement number system to be doing better than this 1's complement and sign magnitude. There are of course other advantages that we will see later. Let us see. So, this is the thing, that is given n bits, what is the range of my numbers in each system. The 3 bits signed minus 3 to plus 3, 1's complement minus 3 to plus 3, 2's complement minus 4 to plus 3. So, if you are given 8 bits, then signed is minus 127 to plus 127, 1's complement minus 127 to plus 127, 2's complement is minus 128 to plus 127. And this is the rule that I was talking about, formula for calculating the range. Signed and 1's complement is minus 2 to the power n minus 1 minus 1 to 2 to the power n minus 1 minus 1, and for 2's complement it is minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. So, this way we can have ranges. Okay. So, how do I derive 1's complement? For 1's complement, given a positive number x 1, x n minus 1, x n minus 1, these are the individual bits of the number x n minus 1, x n minus 2 and to x 0. The negative number is given by this x n minus 1 bar, x n minus 2 bar up to x 0 bar, where x bar is actually 1 minus x. So, x n minus 1 bar is 1 minus x n minus 1, like that. So, it is because of the fact that from the definition of 1's complement it says that it is from the definition of 1's complement it says it is 2 to the power n minus 1 minus x. So, this 2 to the power n so this 2 to the power n minus 1 is all 1, and so 2 to the power n minus 1 minus x is 1 all 1 minus this. So, naturally all the bits are getting complemented. So, for 1's complement, so we can get the number the 1's complement representation of a negative number in this fashion. For 2's complement, the operation is like this, that we have to the negative number is the sum of its 1's complement and 1. So, we can prove it like this, that for 2's complement this is the formula 2 to the power n minus x. So, it can be written as 2 to the power n minus 1 minus x plus 1. So, now this part 2 to the power n minus 1 minus x. So, this is the 1's complement. Okay. With that we are adding this 1. So, 2's complement is basically the 1's complement plus 1. So, these are some examples like x equal to 9. So, this is the or number 9, positive number 9. So, if you take 1's complement, so I will be getting this one. So, 31 minus 9 is 22. So, you can check that this number is really 22. So, it is 1, 2, 4, 8, 16. So, 16 plus 4 20 plus 2 22. So, that is 31 minus 9. 2's complement of minus 9 is 22 plus 1. So, that is 23. Okay. So, that is 32 minus 9, so that is 23. Similarly, here for the 13 also we can get its 1's complement as 10010, 2's complement as 10011. So, this way you can do this, you can prove this 1's complement and 2's complement rules for doing the purpose. So, 1's complement implementation is very simple. So, we are not yet familiar with these symbols, but we will see after a few classes that they are actually the inverters. So, inverter means if you whatever value you give, it just complements that bit and produces the output. So, if you give a 1 here, you will get a 0 here, if you put a 0 here, you will get a 1 here. So, that is what we need for 1's complement. So, for 1's complementing, the hardware is very simple, you just do this thing. But for 2's complement it is not that simple, because for 2's complement after doing this you have to have some adder which will be adding a 1 with this. So, that way the 2's complement hardware is going to be a bit complex compared to 1's complement. But anyway, 2's complement is fine, 1's complement is fine. Now, whenever we are doing some arithmetic operation in 2's complement, suppose we have two positive integers x and y as input. So, we want to do some operations on x and y. So, for doing the operations, first we represent the operands in the 2's complement form, and then we sum up the 2's operand and 2 operands and ignore the bit n. So, we do not need to consider whether it is they are addition operation or subtraction operation, like say x plus y. So, there is nothing to do. So, that is simply the operation is x plus y, but this x minus y, what we do is that we do not use a subtractor, rather this minus y is represented in 2's complement form. So, we have got the number y with us, the positive y with us. So, we take the 2's complement of this y. So, 2's complement of 2's of y is 2 power n minus y. Now, when I so if you just simplify it further, so it is 2 power n plus x minus y. So, if this number turns out to be negative, then it will be subtracted from 2 to the power n directly. So, you will directly get the 2 power n representation. So, basically so you remember that if a number is negative, then suppose I have a number a which is a negative number. So, it is represented as 2 to the power n minus a in the 2's complement notation. Now, you see that I am doing this x minus y. So, what I am doing? I am taking 2's complement of this y. So, accordingly I am getting this value 2 power n minus y. Now, after doing this operation, if the number is positive, then there is no problem, but if the number is negative, okay. So, if the number is positive, then this 2 power n. So, this 2 power n is basically so if you look into this individual bits, okay, let me take a fresh page. And so, if I have got say n equal to 4, fine. So, if n equal to 4, then I have got the bits 0, 1, 2, 3, and this bit is the 4th bit. So, that is basically for if you look into the corresponding weights. So, this is 1, 2, 4, 8, 16. So, this is basically this is equal to 2 to the power n, this is equal to 2 to the power n minus 1, this is 2 power n minus 2 like that. Now, the operation that I was doing there, the operation that I was doing there is this one. So, 2 to the power n plus x minus y. So, this 2 to the power n, so where is it going to affect? So, it is 2 to the power n is represented by this one, fine, plus x minus y. So, if x minus y is a positive quantity, if x minus y is a positive quantity, so it will be restricted to these 4 bits only. So, it is not going to affect this bit. So, whatever the bit is coming, so if I simply ignore this bit, then I will get the sum, I will get the result x minus y. If this result is negative, if x minus y is negative, then of course, there is no problem, because then this whole number is going to be 2 power this as per the representation. So, this is 2 power n minus of x minus y. So, I am getting the result directly. So, if the number x minus y is negative, then I am so by doing this addition, I am what I am essentially getting is 2 power n plus minus of x minus y. So, I am getting the same result. So, by doing this subtraction, instead of doing this subtraction, so if I do addition, then also I am getting this subtraction done. Okay. So, then this minus x plus y, if I have to do it, I do not need to do subtraction, I just take 2's complement of this x, which is 2 power n minus x, and then with that I add y. So, as a result I will get 2 power n plus minus x plus y. The same logic, if this minus x plus y is a positive quantity, then this nth bit can simply be neglected, and if this result is negative, then this will be, this is anyway the 2's complement representation of that negative number, and minus x minus y. So, this is I am taking the 2's complement of them and then doing the addition. So, again I am getting the same thing. So, this is 2 power n plus 2 power n minus x minus y. So, that is the 2's complement representation. So, whatever we are doing, whenever we are doing this subtraction operation, so I can just take the 2's complement representation and do the addition operation. So, for example, this one, say 4 minus 3 is equal to 1. Are we getting it by the formula that we are doing? So, 4 in 2's complement is it is a positive 4. So, this is 0 1 0 0, 3 is 0 0 1 1. Now, I need minus 3. So, 2's complement representation of that is 1 1 0 1. Now, if I am adding now I am adding this. Okay. So, this is the addition and this is the result. Okay. So, after doing the addition, so if we discard this, since the result is since this so we discard this extra 1 at the left. So, this extra 1 at the left is discarded. So, which is 2 to the power n from 2's complement of minus 3. So, and this b n minus 1 bit is 0. So, the result is positive. So, I get a positive number 0 0 0 1. So, this bit can always be neglected. So, we will see with another example, like say minus 4 plus 3, that is equal to 1. So, how is it happening? So, 4 is 0 1 0 0. So, minus 4 is 2's complement representation is so this is 1's complement plus 1. So, 1 1 0 0, 3 is 0 0 1 1. So, 1 1 0 0 plus 0 0 1 1. So, this produces this. Okay. Now, there is no carry produced here to be neglected. So, that carry is 0. Now, you see that since this bit is 1, so this means that this is a negative number, and if you want to get the original the decimal number. So, what you do is you take the 2's complement of this. So, this is 0 0 0 0 plus 1, that is 1. So, our answer is minus 1. So, if the leftmost bit is 1, so that means it is a negative number, and if you convert it if you convert this into its 2's complement. So, you will get the corresponding positive number. So, here I am converting this 1 1 1 1 into 2's complement. So, I am getting 1. So, which is the corresponding positive number. So, in this way we can convert so I have never done any subtraction operation, though it was necessary that I will be doing a subtraction operation of 3 minus 4, but that was not necessary. What about 1's complement operation? So, 1's complement operation is a bit complex. So, here we have got if we have got two input integers x, positive integers x and y. So, first of all we represent them in ones complement, we sum the two operands and we subtract 2 to the power n minus 1 if there is a carry out left. So, in case of 2's complement we did not have to do anything. So, if you represent a 2's complement then sum up, so it was over, but in 1's complement it is not over at that point. So, if there is a carry then you have to subtract 2 to the power n minus 1 and the result will be in 1's complement format. So, this x plus y is x plus y, x minus y is x plus. So, this is 1's complement and then you are getting this thing, and after that if there is a carry then you have to subtract 2 to the power n minus 1. Let us take an example, suppose 4 minus 3. Okay. So, 4 is 0 1 0 0, 3 is 0 0 1 1. So, minus 3 in 1's complement is 1 1 0 0. Now, we are adding this. So, after doing these additions you see there is a carry. So, carry 1 is generated. So, it says that to get the result you have to subtract 2 to the power n minus 1. So, 2 to the power n minus 1 is, so you have to subtract 15 from here. So, after subtracting 15, so this value is 16. So, 2 to the power n minus 1 is 15. So, from 16 I have to subtract 15, I will get a 1. So, we discard the extra 1 at the left which is 2 to the power n and add 1 at the first step. So, this is the process of subtraction. So, you discard this. So, that way you are losing this 16. So, you are subtracting 16 and then you are adding 1. So, essentially we are subtracting 15. Okay. So, essentially we are subtracting 2 to the power n minus 1, that is 15 in this case. So, another example. So, minus 4 plus 3 is minus 1. How is it coming? So, 4 is 0 1 0 0. So, minus 4 1's complement is 1 0 1 1, 3 is 0 0 1 1. So, you are doing this addition. So, after doing this addition it comes 1 1 0 0. Now, so there is no carry generated. So, I do not have to do anything. So, no that 2 power n minus 1 subtraction, that is not necessary. So, it is the, so this itself is the number that I have got, but it is in the 1's complement form. So, to get the actual number what you have to do is that you have to convert it to 1's complement, that is 0 0 0 1. So, that is 1, but since this bit is 1, so it is a negative number. So, the value that you get is minus 1. So, if the leftmost bit is 1, so you are getting a minus 1 here. So, the rule is this one, that after doing the summation, if there is a carry then you subtract 2 power n minus 1. In either case the result will be available in 1's complement notation. So, this way in this example there was a carry generated. So, we had to subtract 15, and for subtracting 15 the clever way that we did is we ignored this one. So, as a result I have subtracted 16 and then I have added, I have turned on this, I have added 1 at the least significant position. So, that way I have made plus 1. So, minus 16 plus 1. So, actually 15 is subtracted. So, in this case since this carry was generated, so I had to subtract 15, but in this case you have got there is no carry generated. So, no subtraction is necessary. So, this result is fine, but only thing is that to get the corresponding value, to understand what is the corresponding value. So, we have to convert it, take it as 1's complement. You take the 1's complement of this, so that is 1, and since this bit is 1, so it is a negative number. So, it is minus 1. So, minus 4 plus 3 is minus 1.